8, 9. Hello and welcome back to Calculus 3, section 13.3 on dot product. Dot product is the way to multiply. You already know one-dimensional dot product. So if you are talking about 1D dot product, that's going to be your 3 times 5 equals 15. You are familiar with multiplication on the number line. So if you have one-dimensional input, which is 3, and then another vector, one-dimensional input, 5, 3 times 5 is 15, and your one-dimensional, this is not ID, this is 1D. Maybe I should put, I don't know, one-dimensional dot product, right? Today, we are interested to learn the two-dimensional dot product, three-dimensional dot product, and it can be extended to n-dimensional dot product, which you cover if you go to linear algebra. We only care about 2D and 3D in this class because the entire course is about third-dimensional calculus with certain excursions into 2D or 4D. If you take a triple integral of a function, you are working in 4 dimensions. But that's going to be later on, and it's going to be laughable of how easy it is. It sounds awful, but it isn't. So one-dimensional dot product is just your basic multiplication you already know. The goal for us is to learn what's happening with 2D and 3D. So to go to 2D now, and we said we're going to call that R squared. So two-dimensional dot product is defined one way and computed another way. We are going to have a lot of that in Calculus 3 when we use the definition to make sense of things, but then we use different formula to compute because it will be much easier. So let's start with computation. First, and this is stuff that you need to know. If you want to multiply two vectors, and in this case, these vectors will be two-dimensional, you will be multiplying u1, u2 with the vector v1, v2. And that is, you multiply u1, v1, and add u2, v2, and the answer for this would be a number. I'll just write that as a number, in parentheses, scalar. So you are not getting a vector back. When you multiply in a dot product, you multiply two vectors, you will get you will get a scalar. So this is the way to compute the dot product, and the example for something like this would be, let's say, 4, -3 dotted with 2, 8. You will have 4 times 2 plus -3 times 8, which would be 8 minus 24 equals -16. So the dot product is the way to multiply two-dimensional, three-dimensional, or whatever dimensions you have. So to multiply vectors, and the answer is going to be a scalar quantity on the other end. Now, to define the dot product, the official definition is actually doubling as the formula to calculate angle between two vectors. So the definition for the dot product is that u dot v is equal to magnitude of u, magnitude of v, times the cosine of the angle between the two vectors. And you guys can transform this formula into a formula which calculates angle between two vectors, which is one of the formulas that you need to know. And that formula would be theta equals inverse cosine of u dot v divided by magnitude of u, magnitude of v. Now, this is one of the formulas that you need to know because angle between two forces is important. If you are pushing an object with your friend, let's say it's a fridge, right? It's important on which angle you are pushing, otherwise you will be slacking. Or you'll be doing more work, depends on what your friend does as well. So the idea is to be able to calculate the angle between two vectors. So the accompanying diagram over here would be to just draw two arbitrary vectors u and v and call the angle in between them theta. Because we did call angle of each individual vector theta, and it's just not the same thing. So we can calculate the angle between two vectors, and again, that angle would be important. You can think about, let's say, a huge tanker ship, right, in the lot of, or any cargo ship, right? There's a lot of stuff on it. And then when those ships are close to the shore, generally they are pulled by tugboats. So you will anchor two tugboats, which are smaller boats that will be pulling this big ship in, and then there is the angle in between, because the tension in each one of these cords that are used to pull, they are whatever material, right? There will be a tension in these cords, and you want to know how much tension. That would be your force, so those are your vectors, but then there is this theta in between those vectors. You are making sure that as these guys are pulling this way, right, because they are moving that way and they are pulling, then the tension in a cord is, right, remember, for every action there is equal and opposite reaction, so sum of all forces has to cancel out. The reason why you are able to sit on that chair is because your weight is pushing down, which is the force pushing down. The chair is pushing with the same and opposite force up, and you are able to sit on a chair. Now, if your force is 700 pounds pushing down a chair might not be structurally sound to push up with the equal and opposite force, right? Which is why it's important to check at least for me, it's important to check the weight of the chair before I sit on it. One. Good thing also to check is about the elevator, right? You know, we've all been there, right? You see someone walking down the hallway and say, hey, close the door, close the door, close the door. Okay, good. I'm going to live today, right? So those are the basics of the dot product. You have the way to compute. Very simple, multiply x components together, multiply y components together, and then add them up. The definition for the dot product is given by the formula from which you can extrapolate the formula for the angle between two vectors that are in question, u and v. Now, another really cool feature is to realize that cosine of 90 degrees is 0. Now, remember that the vector v and vector u are both non-zero vectors. If they are non-zero vectors, they are going to have length, which is magnitude. So, as you look at the formula, u dot v is equal to magnitude of u, magnitude of v, times cosine theta. If theta is equal to 90 degrees or pi over 2 radian, then cosine of pi over 2 is 0. And that would make u dot v. That would make u dot v 0. So now we see that since u and v cannot be 0, since the vectors are non-zero vectors, u and v have to have some value, whatever it is, 0.2 or 10 or 100, doesn't matter. They're non-zero. So we can write a very important and very useful theorem from this realization, and that is that if the dot product is 0, vectors are perpendicular. And it goes back the other way as well. So if the vectors are perpendicular, dot product is 0. If the dot product is 0, vectors are perpendicular. For that purpose, we use the wording if and only if. So we say vectors u and v are perpendicular if and only if u dot v as a dot product is equal to 0. As I said, very useful, very important theorem. We will use it to define many things as we go. Well, not many things, but some of the things as we go along, and it's going to be useful to solve a whole bunch of problems. I am going to just make a note here that if and only if works both ways. If then works only one way. Since you are in Calculus 3, you all passed Calc 2, and you are familiar with the theorem that tests series. It's called either the Divergence Test or it's called the N-term test. And that one says that if the limit of the sequence is different than 0, then series is divergent. That's the if-then. It works only one way. You cannot go backwards and claim convergence by this test. It makes no sense. It's called divergence test. It can only test for divergence, and that's the end of the story. So for that particular theorem, you have if the limit of an as n goes to infinity is different than 0, then summation an is divergent. That is the one-way statement, right? If then. Now, our statement here with the dot product and perpendicular is if and only if. That means that it works either way. If you have a dot product to be 0, it immediately means that vectors are perpendicular, or if you know that the vectors are perpendicular, you know that the dot product is 0 without computing it. So anytime you see if and only if, you are allowed to read that theorem back and forth, and you can use it in either way. But if you have if then, it's only one way, and you can never go back. Like to say whatever else you can come up with that will be wrong, right? So don't do that. For higher dimensions than 2, the word perpendicular turns into orthogonal. So perpendicular is the word that is reserved for 2D when two lines are at 90 degrees. If you are working on 3, 4, 5, or whatever amount of dimensions, use the word orthogonal. Now, the word orthogonal is also good for 2D, so you can just use orthogonal all the time without worrying whether it applies for some dimensions and not for others. So you can just use the word orthogonal 100% of the time. You are allowed to use word perpendicular for 2D. Okay, so I will ask you to, real quick, find the angle between vector u as 3, 8 and vector v negative 1, 6, whatever. So find the angle. Now the answer is going to be probably disgusting decimals, and you are allowed to give the answer in degrees. In this case, your calculator should always be set for radian calculation if you are graphing or calculating stuff in mathematics, except for one case, and that is when the math problem is asking you to compute the angle. That's the only time when you might provide the angle in terms of the degrees. Everything else is done in radian, and the reason is the only way mathematical formulas work is if you're using radians. There are no mathematical formulas where you are plugging degrees. That doesn't exist. All of the formulas, if you see theta, you are plugging in radians. So anytime you are trying to graph something on your calculator or software or whatever, and you type the function in and you see nothing, first thing to make sure is that you are in radians, because graphing works radians only. I mean, you can force it to work in degrees, but it's just 360 times. A lot of annoying calculations you should be required.
said V would be back for 37. Okay. I said error. I used the right tool. No, radian. Oh,
all right, let's take a look. So we have the formula that angle between two vectors is the inverse cosine of u dot v divided by two magnitudes. Now, I did not make sure that these numbers work out nice. I just put up whatever, so let's see how disgusting this gets. 3 times -1 is -3 plus 48. The absolute value of magnitude of u, that's 9 plus 64, is square root of 73 times the square root of 37. Oh, this is going to be epic over here. Is inverse cosine of 45 divided by the square root of 73 times 37. Nice. So now you go to your abacus, change to degrees. This is pretty much the only time you're going to do that. Then second quit. Okay, inverse cosine of 45 divided by the square root of 73 times 37. Wow, 30.002. So just call it 30 degrees. Nice. Cool. Properties of the dot product, something that the honors should be able to prove. Again, plug and chug. So yesterday we had those 10 properties for vectors, for vector operations. Today we have 3 properties for dot product. Dot product is commutative, so u dot v is the same as v dot u. Very simple to prove this one. You do both dot products and you will claim the answer on the commutative property of the basic multiplication when you add the components. And then we have c u dot v, so c is a constant, right? There is no arrow up on top of it. So this is going to be associative property. We can associate c to u and then dot v, or we can associate c to v and then dot it into u. Number 3, u dot v plus w, which is u dot v plus u dot w, which is the distributive property. The way you solve any of these in a proof is you can use 2D. In linear algebra, you learn the n-dimensional proofs for all of these. Now you can just use 2D. If you really want to annoy yourself, use 3D because it's more writing. Each vector u will be replaced by u1, u2, each v's, v1, v2, and then you just grind through calculations, making sure that the left side and the right side of the equation are the same. So those would be the extra problems for the honors, if you choose to do that. So now we are going to take a look at applications of the dot product, and after that we're done. So we're going to take a look at 2 applications. The first one would be the orthogonal projections. And the second one is going to be a physics problem where we consider forces and we do the dot product to calculate work. There are obviously countless examples of using the dot product in physics. We're just going to do the simple one. So let's talk about orthogonal projection first. If you are interested in full derivation of orthogonal projection, it's listed in a book. And you can talk to me either after class or so if you are confused with any of its details. I am going to focus on the use of it and calculation in class. And as I said, if you want more info and stuff, let's talk to me later. So I'm going to have some vector u and then a vector v. And I would like to calculate. So we want to know which part of vector u is in the shadow of vector v. So what do I mean by this? If I am to shine the light from above vector u, there is going to be a shadow which is a part of u that will be cast by vector v. That red line there is a projection of vector v onto vector u. So your base vector, guys, the base vector, that one that you are projecting onto, is going to be here. Now, the notation follows log notation. Remember when they say log of base 2 of 7 and then base 2, that's the small number on the bottom. Well, vector u is actually a base for this projection because it's the one that will carry the shadow. So you can think of that if you are having problem or have a issue remembering which one is which. So you are projecting v onto the base vector u. Log of 2 is 10, or log 2 of 10, right? So that's the base. The small one is the base. Projection of vector v onto u. So I'm going to spell that out. Projection of v onto vector u. So that's the way we read this. There are a lot of applications for something like this. I can give you a very quick example. We are going to work this out later, but look at this, guys. If I want to push an object on the surface, and I push this chair forward, like it has wheels, so it moves easy. But observe the way I am applying the force. I'm applying a force at an angle. Now, this particular force that I am applying has two components. Has a component that is pushing straight forward, and has a component that is pushing down, right? Because this arrow here can be decomposed into the vertical down and the forward. Now, is this chair going into the ground at all? No. Which means that the entire component of the vector, which is pushing the chair down, the component of the force, which is pushing the chair down, the floor is pushing the same and opposite up. That's called waste, right? So the only component which is pushing the chair at this moment is going to be the projection of this vector onto the flat plane, which will give me exactly the sole vector which is doing the work, which is the force, right? Force is the work times, that's the application problem we're going to talk about. So is this a good way to push a heavy object? The answer is no, because you are wasting some of your energy on trying to push the object into the ground, and the ground is pushing up with the same and opposite force, and you're wasting energy. If you're able to position yourself so that you are parallel to the surface that you are pushing on, 100% of your energy is force, which will do the work to make the push. So, hello mechanical engineers, right? When you're designing stuff, you need to make sure, right, that all of that works out and you are not wasting energy, power, whatever, with pushing or pulling in directions where there will be a lot. Sometimes can be avoided, right? So the portion of it, and that all goes into efficiency. Our gas powered cars, the ones that are pretty much all of the cars on the market, are one of the worst and most wasteful machines we have. They're about 25 to 27% efficient. It's one of the worst things we have in terms of machinery. That means that 3/4 of the money you pay at the gas station is a waste. And only 25% is what drives you from point A to B and runs your air conditioning and music and lights and other stuff that you're doing in a car. 75% is heat and noise and all of the other stuff that we don't use. That's how pathetic that technology is, which is called a car. Tesla, however, is 98% efficient. You know what that means? 98% of money you put into that battery tank is using to drive around, and only 2% is the waste of energy, which is why Tesla is so much superior to any car and ever will be. And the sooner we get rid of these cars that we have today, as a species, we'll do much better. So the price of Tesla is obviously high because they need to cover their production costs of brand new technology and all that kind of stuff. But when you think it's not just that you are wasting money, that you're saving money because electricity is cheaper than the gas, you also save 3/4 of your gas money, which is actually converted into efficiency and driving. And that's one of the parts that, you're always going to have someone who says, well, yeah, I like the sound of the engine. Perfect, get a horse. That was the previous iteration of your car. All right, car is almost 150 years old technology, right? We need a new one, right? So that would be an electric car is the next iteration. I mean, you still have people obsessing about horses and stuff, so you can never make sense of the wider population. So don't waste your time and hold your breath that everyone will make sense. They won't. What is the formula that will calculate projection vector as you are trying to find which component of the, let's say, force actually does the work? So projection well, now it's given u onto v, so it's opposite of what I have there, whatever. It's going to be u dot v divided by v dot v, everything dot v. So this is the formula, and if you swap u and v to match what I have written up there in red. So projection of vector v onto vector u, if you want u to be a base, then you still have u dot v, and now you have u, u, and u. So, you know, I'll just say or. Just be mindful what your base is, right? In this case over here, base is vector v. Over here, base is vector u. Now, that is going to be your responsibility to figure out which one is base. When you see the problem, you have formula is, look at this, all v's, base is v, all u's, base is u. So, get that, right? And to compute the vector projection, you are expecting to get the vector, right? And you are going to get a vector because the dot product in the numerator gives you a number. The dot product in the denominator gives you a number. So when you divide a number with a number, which is a scalar, right? You get a number, and then number times the vector gives you a vector, which is in the direction of the base vector, which is why these two always match. They always match, because it needs to preserve the direction of the base vector. Your projection is going to be lying on the projection vector. So if I have, let's say, base to be a vector v, and you have vector u to project on it, you will drop 90 degree, and this vector here is the projection vector. Right, so it doesn't matter on which angle, right, the whole deal is. The important aspect is that the projection vector and the base vector are always the same direction, because the projection vector is the part of the base vector. Right? I said that on the first sentence here, right? The shadow of the vector, and we see that the projection vector always sits on the base vector because that's where the shadow is. So let's take a look at example. They want you to compute projection. Let's go with a homework example. So, trying to find something is not forever. Oh, yeah, whatever. So, problem 36 gives you vector u is 10, 5, vector v is 2 and 6. They want the projection onto u. So projection of u onto v. Projection of u onto v. So you will be using the v equation on top for this calculation.
but the form. Yeah, I think so. But then you have to have access to start responses, of course.
All right, so projection of vector u onto vector v is going to be u dot v divided by v dot v, everything times v. So you have three v's over here because you are projecting onto v. 10 times 2 is 20, plus 5 times 6 is 30, divided by 4, plus 36, everything dot 26. This is 50 divided by 40 dot 26, which is 5/4 dotted into 2, 6. Now you can cancel by 2, get 2, 1, and 3, and the whole thing is going to be 5/2 and 15/2. And it's a vector, so you have to have a spiky brackets. This is good?
Yeah.
Great. That's the projection. Very simple. What's the shadow of the vector? Right? The next concept, also application, would be concept of work in physics. Generally, schools have two levels of physics. There is what they would most call general physics, which is algebra and trig based, and then analytical engineering or whatever, university physics, which would be calculus based. Clearly, calculus based is the one that it's needed for all of you fine engineers. Now, in basic physics, right, algebra and trig based, work is simply defined as force times distance, right? So work is equal to force times distance, and in your basic physics is just denoted as W is equal to F times D. Now, that is all cool when you are dealing on with the objects that are sitting on the floor and you are just pushing forward and with the force that is parallel to the floor. So when everything is, so this formula covers exactly one case. Here's your flat ground, non-inclined ground. Here is your object which you are pushing, so it's some kind of crate. And here is the force that it's applied to it, and it's going to cover some distance d. So this is the cheapest possible formula. You understand this either in the middle school, we're all good. But we have inclines, we have forces that come to the box at an angle, we have all of these other things that we can make this calculation impossible with a formula so basic. So we actually want to define work still as force times distance, but it's going to be force times the distance. And now these two are vectors. And when you have this defined this way, now you're allowed to push at any angle. Remember when I pushed the chair from standing upright and push the chair from being in line, right? So that case, so this formula will cover both of those cases. And then also your displacement distance d, right? You can be on a flat ground, but you can go up the incline, down the incline, or whatever. So you are not only restricted to be on the flat surface. So now, when you think about this, you know that you can rewrite the dot product as the magnitude of the force times the magnitude of the distance times the angle between them, which was our definition for the dot product. And this would be the formula that you guys use to calculate work when you have some kind of object to push up the incline or whatever. So let's go and take a look at the word problem or something that a constant force. Now, if you don't want a constant force, you can involve integration and calculus. So a constant, this is problem 44 in the homework, a constant force F that is given as 432 in newtons, so capital N, moves an object from the origin, which is 0, 0, 0. Oh, this is a 3D. Wow, that's fine. To 8, 6, 0. And distance in meters. Distance in meters. So clearly, if you're using newtons, you should be using meters. If you're using pounds, you will be using feet. So what is the work done to push the object for this distance? Well, we all know that we are supposed to calculate the distance vector when you subtract terminal point minus initial point. That was our first lesson of the course. So the distance vector is 8, 6, 0 because we are at the origin. 8 minus 0, 6 minus 0, 0 minus 0. So we have our distance vector. We have our force vector. So now we know what to do. We are going to work out the dot product between these two, and then we can also find the angle if we want to. So work is going to be the force vector 432 dotted with the distance vector. Now, I did not give you the formula to multiply these 3D vectors, but guys, you can extrapolate it. You just need to multiply these and add them, right? So if you are working on a dot product for the 3D vectors, which is u1, u2, u3, dotted with v1, v2, v3, it would be u1, v1, u2, v2, u3, v3, and that's also going to be equal a number. So this would be your 3D way of, so this is R3 dot product, right? R3. So now you know that 4 times 8 is 32, plus 3 times 6 is 18, plus 2 times 0 is 0, for the 50 Newton meters. So work done is 50 Newton meters in this case. So now everything that we have done so far for 2D obviously holds for 3D. You just simply make your case over there that the throw-dimensional, and as I said, it works in any dimension, but that's going to be left for your linear algebra to take care of. Yes?
So for that problem, do you just assume that the angle is 0 degrees? Do
We don't have to assume anything because the dot product, the work is force times the displacement, right? So and we have them as vectors. In some cases, they will say that you are attacking at the angle of 30 degrees, in which case you will be using the formula that contains degrees. Because some problems are stated that you need to push an object at 30 degrees 2 meters. Well, this is your 2 meters because it's the length, just the length, and your 30 degrees incline goes in a cosine, and you have the force, which you find the magnitude, and you would use this. So it's like two flavors of the problem. One flavor of the problem will give you the two vectors or ability to get them easy, like we had, or some other problems. I think here it is, problem 42 or 43. A sled is pulled 10 meters with a 5 Newton force at an angle of 45, right? So in that case, you would be using the boxed equation. Our problem here gave us the vector and ability to find the other vector like this, which means you can use the top equation. Right? So it's one or the other, and it depends on. Now, in both cases with extra work, you can use both equations, right? Because in this case over here, I have both vectors, right? If I have both vectors, I can do the cosine equation to find the angle, and then I can find both magnitudes and use this still. It's just, equivalent of coming to this college through Holland Tunnel, right? Because we have direct run. So you use one or the other. It just depends on what info you're given. If you're given an angle, use the formula with angle. If you're given vectors, use the formula with vectors. That's it. The dot product, the meaning, the use, the calculation, projections, application. Let's take a break, and after the break, we will work on the cross product.